Welcome back, everyone. So in the previous video, we introduced this concept of hybrid orbitals. Orbitals that are used to explain the bonding geometry and bonding shape of a particular molecule with respect to its valence electrons. In the example we gave in the previous video with methane, in that example, to explain the tetrahedral arrangement that is seen in that molecule, and that is also predicted by the Lewis dot structure, we would have to hybridize or mix an s and 3 p orbitals from carbon to produce 4 sp3 orbitals. Those hybrid orbitals, which each have 1 electron due to the hybridization process, that promotion of the 1 2s electron to a 2p orbital, that hybridization produces 4 sp3 orbitals, shown by the gold-shaped leaf here. And those orbitals that now have 1 electron can overlap with a s orbital, s atomic orbital from hydrogen to produce the covalent bond. So this sp3 hybrid orbital concept for methane and for other molecules fits with what is predicted with the Lewis dot structure and VSEPR theory. So this concept of hybrid orbitals we used to create these sp3 regions of space. We could also use these concepts to form something called sp2 hybrid orbitals. BF3 is an example. If I was to give you the Lewis dot structure for BF3, based off of what we've talked about so far with regards to VSEPR theory and our electron configurations, we would look at that Lewis structure and say, oh, yep, that is an AX3 VSEPR notation, which just has a trigonal planar geometry with 120 degree bond angles. But looking at that electron configuration for boron, that central atom, I've only got 1 electron in a 2p orbital that's accessible for bonding, which is shown also in this energy diagram. But we can visualize or support this Lewis dot structure and VSEPR notation by not thinking about the just s and just p orbitals participating in covalent bonding, but hybridizing them so that I take a 2s electron and promote it to one of the 2p's. Doing that, I now have 1, 2, 3 resulting hybrid orbitals that are of lower energy than the 2p orbitals. And these sp2 hybrid orbitals, of which there are 3, because I have mixed 1s and 2p orbitals to give sp2, these 3 sp2 orbitals are now available to accept that 1s, or to accept that electron from the p orbital of fluorine. One other note to make about this example, you notice that in hybridization, sometimes some orbitals remain unhybridized because they are not participating in bonding. So for BF3, we have 3 sp2 hybrid orbitals, but we also have a vacant or an unhybridized p orbital still occupied on boron. So these sp2 hybrid orbitals can explain and support what we see with VSEPR notation and the Lewis dot structure. And that's shown here where we see boron and its sp2 orbital overlapping with the p electron in fluorine in that atomic orbital. And that bond that is formed, that single bond, is also called a sigma bond. So sp2 hybridized orbitals, same concept as for sp3, but with sp2 orbitals, we have 1s and 2p atomic orbitals mixing to create the sp2 hybrid orbitals. And we can use a similar thought process with sp hybrid orbitals. So here, if I was to say give you the Lewis dot structure for BeF2, you would easily see, oh, this is an AX2 VSEPR notation that has a linear geometry. Looking at the electron configuration for beryllium, it's hard to see how we can have just 2 bonds, but if we do a hybridization process by taking one 2s electron and taking that 2s orbital that is now singly occupied with one of the 2p orbitals that is now singly occupied with an electron, we get 2 sp hybrid orbitals that are now available to accommodate the p electron in fluorine, which is what we see in the previous slide and is what is seen here. That sp hybrid orbital overlapping with the 2p orbital in fluorine to produce a sigma bond. So those are the 3 kinds of hybridization orbitals that we've talked about so far: sp3, sp2, and sp. Those hybrid orbitals seek to explain and support the bonding that is seen and predicted with VSEPR and Lewis dot structures. In the next video, we're going to talk a bit about hybridization that is hypothesized with d orbitals, those orbitals that are used with the transition metals.